Here begins a lesson on the idea of concentrations of solutions. Concentrations can be either qualitative with the terms dilute versus concentrated, or they can be quantitative in terms of moles per quantity of solvent. So here we're just reviewing a molarity unit and introducing a brand new unit known as molality. Since solutions do indeed have a variable composition, we can have a little bit of solute in a solvent to create a dilute solution, or we can have quite a bit of a solute in a solvent to have a concentrated solution. The term concentration simply refers to the amount of solute in a given amount of solvent. And occasionally, what we talk about with quantitative terms, most often we use big M, of course, molarity units, but we're also going to introduce a little m, molality units as well. So when we begin, we're going to review some molarity and then introduce a whole new concept known as molality. I have a calculator out. This is going to involve some practice problems together as well. First slide here, in a quantitative term describing concentrations, is the capital M unit known as molarity. We know that to be a given number of moles of solute per liter of solution, and we have had a multiple of opportunities to practice the molarity unit. I do want to stress that this indeed is of the entire solution, and that unit down here is a volume. So when we compare in a next step to a second unit known as molality, keep in mind the familiar term molarity. Boy, they sound similar, don't they? Moles per liter of solution. It's going to describe for us how many moles of solute per liter of solution. So if I'm seeing that we have, for instance, a 2 molar solution, that tells me I have 2 moles of solute in every 1 liter of solution. If I doubled the volume, I'd have half the number of moles. So just a kind of a direct relationship there with quantities, moles per liter. We've also practiced, boy oh boy, a ton in terms of dissociation equations with our electrolyte chapter, chapter 4. Let's suppose we have an electrolyte, calcium chloride. When placed into water, we know that it dissociates or lets go or releases its ions as it becomes solvated or drawn into the water as it forms a homogeneous mixture called a solution. And we've practiced saying, suppose I had, let's say a 0.1 molar calcium chloride aqueous solution. That term dissociates means release. Just keeping in mind the ratio, we'd also have a 0.1 molar calcium, but a 0.2 molar aqueous chloride ion solution. So with this term dissociation, keep in mind that formula units, when they dissociate, these are commonly called salts. We let go of ions and we just keep the ratio there. So a 0.1 molar calcium chloride is 0.1 molar calcium, 0.2 molar chloride. In a while, not just quite yet, but we're going to call this the Van Hoff factor when we talk about colligative properties. How many particles are released when we place something into solution? That's going to play a role. Let me get that written there. How many particles are released when placed into water, and boy oh boy, that's going to play a role in our colligative properties section. That might be a brand new word, colligative properties, those physical properties that change just because we've added a solute into the solvent. Solutions have certain physical properties, things like boiling points, melting points, things along those lines that change just by creating a solution. That Van Hoff factor, we'll write that later in our notes. I'm just seeding that word for a future little lesson coming up our way shortly. Van Hoff factors tell us how many particles play a role in the dissociation. Calcium chloride, when it's released, I can see 3 total number of particles in solution, one of them being calcium, 2 more for chloride. A total of 3 particles will be its Van Hoff factor. And this is just letting me talk a little bit about something coming up future here for colligative properties. It's going to get a little symbol I, and it's a cursive I, so I'm trying to draw a little I there like that. Oh, just to kind of show, what if we had aluminum chloride, AlCl3, dropping that into a solution of water to create an aqueous ion of aluminum, and we'd have 3 aqueous ions of chloride. The total number of particles when this salt dissociates, I see 4. The Van Hoff factor, 4 total particles. So this just let me kind of seed a little lesson coming up talking about dissociation of molarity. A 0.1 molar aluminum chloride would be 0.1 molar in aluminum and 0.3 molar in chloride. That process of dissociation, when a salt dissolves in water and dissociates. We have a new concentration term to introduce in this section. It's molality. Now, I know the most common way a chemist will describe the concentration of a solution is in terms of molarity units. But also, a chemist who really wants to use a unit that does not depend on temperature is going to describe something in terms of a molality unit. Now, let me make sense of that. Because molality measures the amount of solute per kilogram of solvent, notice that's a mass unit. Masses do not change by temperature, whereas volumes will change by temperatures. If you warm things up, they expand. If you cool things down, they contract. Volumes depend on temperature. The molality unit takes out that dependency, and it makes the better unit as we describe colligative properties in our future next step lesson. Little m, molality, you'll see me try to draw that with a little kind of a cursive M to kind of show it's the different unit than big M, molarity, its close cousin. Molality defines the concentration of a solution in terms of the moles of solute per kilogram of just the solvent. I'm going to write underneath here, big M, molarity, moles of solute, just to have it in the same place, per liter of the whole solution. Solutions are built of 2 parts. Solutions take a solute and combine them in a solvent. A solution is made of 2 parts, a solute and a solvent. This is the only factor that we bring into the molality unit. Not the entire mass of the solution, not the solute combined with the solvent mass, but just the solvent alone, usually typically a water solution. So a little different in distinguishing between those 2 units. We've got molarity that considers volume of solution and molality that only considers the kilogram mass of the solvent. Problems are straightforward, but it's a distinguishing determination, a different definition that's going to allow us to convert between molarity and molality units. So let's take a quick peek at our first practice. We want to calculate the molarity. Keep in mind, we have to be careful readers. Molarity is our familiar unit, moles of solute per liter of solution. We're going to dissolve 34 grams of ammonia into 2 times 10 to the 3rd mils of solution, a combined volume of solution. Molarity is moles per liter. I've probably written that way too many times, but hopefully it will sink in. Moles per liter, moles of solute. So I like to begin by writing the number, the label, and the unit of what's given. 34 grams of ammonia. I'll use a mole map conversion to convert my grams of ammonia into moles of ammonia. And it was nice, they provided me with the formula weight, or the molar mass. 17.04 grams per mole. And that's going to convert out from my grams to my mole unit. Now, molarity is defined as moles per liter. So in my next step, I'm going to just set my volume unit under a 1 so I can see that it will end in the bottom. Now let's see here. We have a volume of 2 times 10 to the 3 milliliters. Now I say this, if this is a milli and that means times 10 to the 3rd, those 2 are just really canceling each other. 2,000 millis is 2 liters of solution. Grams over formula weight gets me to moles. Moles over volume brings me to big M, the molar units. Let's see the concentration. Hit with me. I'm going to grab my calculator, hit it with me. I start with my 34. I'm going to divide by 17.04, the molar mass of ammonia, the solute, and the combined volume of 2 liters of our solution. I get 0.9976, pretty close to 1, isn't it? But I'll carry those decimals just to have that distinguishing mark there. So 0.99, I guess I'll go up 1, 0.998 molar solution. Grams divided by formula weight divided by volume is a molarity. What if we're asked to calculate molality of a solution? And that symbol is little m. And I'm going to try to make that a little cursive sign so we can see little m, molality. We're preparing 17.2 grams of ethylene glycol. And this is radiator fluid, C2H6O2. Again, the nomenclature not important, but I like to see the organic words as much as I possibly can. They may or may not appear, you know, it's on the AP exam, but it's sure darn good practice for your next lessons in organic. Ethylene glycol, C2H6O2. Ethyl comes from the 2 carbons. I prepare that with 0.5 kilograms of water in 550 mils of solution. Now, molality, moles of solute per kilogram of solvent. Alrighty. Now, what's the solute? What's the solvent? Well, the ethylene glycol is the solute, and it's being dissolved into water, which is the universal solvent. Alrighty. So let's begin by writing out our number, 17.2 grams of the solute, C2H6O2, ethylene glycol, just so you start to hear those organic names. Radiator fluid, ethylene glycol. When I consider my mole map, what I need to do is to convert my grams to moles, and I do that with a molar mass. So I have to add up C2H6O2 and find a formula weight. Now I don't know that, so let me just take a minute and hit that on my screen. 12 times 2 for the carbon, 6 more on the hydrogen, 16 times 2 for the oxygen. I get a formula weight of 62. Alrighty, 62 gram per mole, the molar mass. When I cancel out, we've converted our grams to moles, and we have a next step where we need the kilogram of solvent, and I'll just set it under a 1. Now here we have mass of water and the total volume of solution. Which number are we going to use for molality? Well, the molality says per kilogram of just the solvent, not the addition of the two, not solute and solvent, but simply the mass of the water already provided in that kilogram unit. Step 1 cancels grams and we're at moles. Moles per kilogram is our molality unit of ethylene glycol. 17.2 divide by 62, divide by 0.5, and my molality is 0.5548. Oh, let's put that down as 0.55 molal. I can write that out. Molal units of ethylene glycol. Now it didn't ask us, but what if it had to convert that into molarity units? In the molarity units, 17.2 grams of our solute, C2H6O2, we can use our molar mass we found to be 62 grams. It's the critical next step that distinguishes the molality and molarity. Molality used kilograms of solvent. Molarity will use liters of solution. So 0.515 liters, and I can hit that for us. 17.2 divided by 62 divided by 0.515 liters, I get 0.5386. I'll carry 2 decimals. Big M, molar units of ethylene glycol. Notice that this term is pronounced molar. The little m is pronounced molal. A molal solution of 0.55 units, a molar solution of 0.54 units. So we have volume of solution for molarity. We have mass of the solvent in molality. This molality unit is being introduced for a very specific reason. When we take our next step with colligative properties, that's the very unit that plays a role in determining how much the boiling point changes or how much the freezing point changes just by adding a little salt into the water. Let's try another one. We're being asked to calculate the molality of a solution by dissolving 34 grams of ammonia into 2 times 10 to the third mils of water. Well, again, just to keep practicing the definition, molality, moles of solute per kilogram of solvent. Water is the solvent, always is, but they gave me a volume reading. No worries, because they've also given me the density of water, which is nice. It's just an easy number of 1. So when I see 2.00 times 10 to the third mils, why don't I just fix that? It's 2,000 milliliters. Get rid of the times 10 to then rewrite it normally. 2,000 is 2 times 10 to the third. Watch how I can use the density. 1 gram is the weight of 1 mil of water, and that's true close to 0 degrees Celsius. By using density, we can convert the volume unit into a mass unit. The mass is identical simply because the density was provided as 1. Now, friends, that's not always the case. Solutions may have a different density. But in this example, the mass and the volume are indeed the same number because the density was equal to 1. Keep in mind when we get ready to do our molality, we need it to be kilograms. 2,000 grams is the same as saying 2 kilograms of water. We have 34 grams of a solute called ammonia. Now the solute is what we have the least of. The ammonia is being dissolved into the water. We'll use the molar mass again to convert from grams to moles, and that's provided for us, just adding the weight of an N to 3 H's. To convert to molality, I set it under a 1 and divide by the mass of the solvent. And in this case, we have the solvent to be water, 2 kilograms worth. Grams cancel with step 1. We get moles per kilogram, which is the very definition of molality of an aqueous solution of ammonia. Hit it with me and be sure I'm doing it correctly. I start with my 34 grams of solute called ammonia. I'll divide it by 1704, the formula weight of NH3. Divide it by 2, the kilograms, this mass of the solvent, 0.9976, I think we had that number a moment ago, 0.998. I'll just leave it with 3 decimal places there. Given the density, we can convert volume to mass readings. Well, here's an example, very similar, but now we're given a density that's not just quite 1. What is the molality of a 16.2 molar aqueous sulfuric acid solution? Interesting. This problem is the direct practice of converting between units, converting a molar unit to a molality unit. Quite a few steps actually. Let's kind of take this slow. The very definition of molarity says that there are 16.2 moles of aqueous acid in the combined volume of a liter of solution. moles per liter. So I just took this number here, 16.2 molar, and I defined it. Moles per liter of solution. Well, one of the things to consider is this entire solution, in order to get out molality, we've got to convert that into a kilogram unit, don't we? So here's my definition of moles per liter of solution. We've got to do a little bit of work. What's the mass of a liter of solution? So let's consider if I have 1 liter, that's the same as saying 1,000 milliliters. And I'm doing that because I see that my conversion here with density involves a mill. So I just want like units. Using that, I can see that if I had 1 milliliter, it would weigh 1.80 grams. That's my conversion, 1.80 grams for every mill of solution. So a liter of solution, how much would it weigh? Well, 1,000 times 1.8 grams is what, 1,800? I just slide the decimal correct. So 1,800 grams of solution. We've got a little more work to do. Consider we've got moles of solute, which we have 16.2 moles. That's set on the top. But what I need is just the kilogram of solvent. This mass, 1,800, is of 2 parts. It's of the acid and the water. The solute and the solvent creates the whole 1,800 mass of solution. When we convert underneath here for the kilogram, I mean, we already know the moles. That's the same, 16.2 moles of the aqueous acid. But what about just the mass of the solvent, which is the water in this case? If the total amount of the weight of solution is 1,800, we could figure out how many of those total grams are coming from the solute because we know simply just a little mole map problem. In other words, we have 16.2 moles already of the acid in there, H2SO4. I can use my little molar mass, little mole map conversion and say, well, 98.08 grams is the mass of 1 mole. Moles cancel and we've converted to a gram. Moles times formula weight. Let's hit that. 16.2 times 98.08, carrying all those decimals. It's 1588.896. Can you round a little bit? Let's say 0.9. Right here, let me change color to emphasize, we've determined this mass, 15.88.9, 1588.9, that's the mass of the solute. Whoops, I don't need a decimal there. I wanted to write 1588.9 grams. The mass of the entire solution minus the mass of just the solute is going to give me the mass of the solvent, which is the water in this case. So if the whole thing weighed 1,800, I'm going to subtract the 1588.9, and it gives me 211.1 grams. That's the mass of my solvent, the water molecule. When I made my solution 16.2 moles of acid per liter of solution, that was the same as saying I took 16.2 moles of the aqueous acid and I put that into this mass in a kilogram, 0.211 kilograms of water. That's my little m. 16.2 moles of acid over the kilogram of solvent, and we'll have our molality. Oh, I didn't write that very neat. The kilogram we determined to be the 0.211 kilograms. Now hit that with me. What do we find? 16.2 moles divided by 0.2111, carry all those decimals, 76.74 molal solution. It's worth digesting this problem. It's a very important problem. How do I convert molarity units to molality units? I start by knowing, by the very definition of molarity, moles per liter. I used the density, this is the density unit right here, to convert, very important step, convert the volume to a mass by using the density. But that mass represents two components, the solute and the solvent. By using a mole map problem, we can determine the contribution of the weight of the solution, just the solvent component, by a mole map problem. We subtract out the mass of the solute to find the mass of the solvent, the water, and that becomes the bottom number in my molality. I'd highly recommend pausing the video, practice this problem multiple times until you feel confident of the steps that we've taken. Ask yourself, how do we convert big M to little m before you proceed in the lesson? Now that we've talked about colligative properties, molality units specifically, we're ready to begin talking about those physical properties of solvents that change when we add a solute to the solution. Colligative properties are defined as those properties whose value depends only on the number of solute particles and not on what they are. Quantity, not identity. The more and more you add of a solute, the more you affect certain physical properties. Doesn't matter what I add, just how much of it I add. The value of the property depends upon the concentration of the solution. That's the quantitative measurement of the solution. The difference in the value of the property between the solution and the pure substance is generally related to the different attractive forces and solute particles occupying solvent molecule positions. In other words, the intermolecular forces become disruptive when I add a solute into the solvent. And I'm going to just say that to add it to the water, the common universal solvent. The intermolecular attractions of a water molecule are hydrogen bonding, the most dominant force. So if I start to remember hydrogen bonding, that strong attraction between the O on one molecule and the H on another, when water begins to align itself, it starts forming these very strong attractive forces between the molecules. When I start adding a solute into the water, suppose I start adding sodium chloride. I have interference between these hydrogen bonds. Suppose as the water begins to unalign with itself and have to realign around the sodium or around the chloride, it's a disruptive force. When we disrupt normal interactions between solvent particles, we change certain physical properties. And those physical properties that are changed are known as colligative properties. Colligative properties are physical properties that change just by adding, let's say, salt into water or sugar into water. Remember, it doesn't matter what I add, it just depends on how much I add. Those physical properties that change include vapor pressure, boiling points, freezing points, and osmotic pressure. the pressure across a semi-permeable membrane. We'll tackle these and talk about why vapor pressure lowers. Because the vapor pressure lowers, boiling points elevate. These are kind of a cause and effect. The freezing point depresses or goes down, and the osmotic pressure begins to increase the more and more concentrated a solution is. Vapor pressure was discussed in Chapter 11, that pressure that's exerted above a solution that's in dynamic equilibrium. Boiling point elevation and freezing point lowering, that's where our molality unit will come in. And osmotic pressure, boy, if you've had biology and talked about osmosis, moving water across a semi-permeable membrane, that actually uses big M, molarity units. Vapor pressure, for our purposes, will not be a quantitative measurement. It's something known as Raoult's law, but it's beyond the scope of the AP curriculum. So just, I believe, 2 years ago, it's been removed. So I've removed it from our notes and turned it into just a discussion and not actually a number crunching problem. Not that they were hard, they're just trying to narrow the scope of what we have to learn. Boiling point and freezing point are calculations as well as osmotic pressure. Let's begin by taking a look at first with a discussion of the vapor pressure. When I think about vapor pressure, a nice picture is actually helpful here. I have a solution and the solvent is represented by the blue molecules and the solute is represented by the red molecules. The term vapor pressure refers to the pressure that's being exerted by the blue, the solvent molecules, against the surface of its liquid in equilibrium. Notice there's a lid on this. This is a watch glass covering a beaker. So I didn't have a lid. These gas molecules just would evaporate out to the air. No exerted pressure would be formed. The more and more and more blue particles that form, the greater the push down on the surface of the fluid. And that's what's called the vapor pressure. As time goes by, this dynamic equilibrium is established. Liquid molecules turn into gas. That's called evaporation. The gas molecules condense down back to a liquid. Gas to liquid is condensation. The more and more and more gas particles above the surface of its fluid creates a pressure against the surface. That's vapor pressure. But what if we open the lid and we start adding more and more red particles into our solution? If we add more and more red particles called solute, we start to create this competition to be at the surface of the liquid here. And remember, evaporation occurs at the surface only. Those blue molecules to evaporate must be at the surface. Think about it. If they're down here at the bottom of the beaker, there's no way they're going to be able to escape and form a gas. They have to be at the surface. But what if I start adding solute and the competition becomes great? The blue molecules get pushed away from the surface and are prevented from evaporating. Vapor pressure drops. And the more and more and more and more I add, the more I prevent the liquid from evaporating. Therefore, the vapor pressure is prevented from even forming. So therefore, vapor pressure lowers when I add a solute to the solvent. The vapor pressure of a solvent above the solution is lower than that of the pure solvent. The evaporation is prevented just by the mere competition to be at the surface of the liquid here. Our second colligative property is known as the freezing point depression. Pure water freezes at 0 degrees Celsius. At this temperature, ice and liquid water are indeed at dynamic equilibrium. The process of liquid turning to solid is freezing. Solid turning to liquid is melting, and they are indeed in a dynamic equilibrium at 0 degrees Celsius. Those processes are occurring at the same rate. If I add a solute, such as salt or sugar, some kind of solute, into the water, it begins to disrupt this equilibrium. And those salt particles, as they begin to dissolve in the water, start to interrupt the hydrogen bonding, the intermolecular attractions between the water. That disruption of equilibrium prevents them from freezing. So a solution that contains dissolved solid freezes very slowly. And the ice that forms doesn't normally contain as much solute. The salt gets left out because it's disrupting the hydrogen bonding. It's why we salt the roads in the winter, salt your driveway, salt your steps leading up to your front door. We place salt on the cement to melt the ice. If water normally freezes at 0, salt water can freeze as much as -5, -7 degrees Celsius and remain a liquid form even though it's freezing outside. It melts the ice by disrupting the intermolecular attractions. And the more and more and more you add, the lower the freezing point becomes. Remember, it depends upon the quantity and not the identity, these colligative properties. We can calculate how much the freezing point changes with a simple formula. The freezing point depression. The freezing point of a solution is lower than that of the pure solvent, and we can calculate that freezing point depression with the following formula. The difference in the freezing point of the pure solvent and the solution is what I call the change in temperature, the delta sign, meaning delta is change, the change in the temperature of the freezing. Can be calculated by knowing the molality, see that little m, molality, times the K constant. That proportionality constant is an experimentally determined constant that tells us how many degrees Celsius does the solution depress for every 1 molal solution. And it's a unique number for every solvent. These are published in tables. Let me show you one. In this particular slide, we have not only KF's, freezing point constants, but we also have some KB's, boiling point constants. We have a list of solvents and their normal freezing points, their K constants, their normal boiling points, and their KB constants. Let me give an example. Let's start with the one that we're most familiar with, water. Water is the universal solvent. Water will freeze at 0 degrees Celsius. When you see the word normal, that means standard conditions, right? At normal atmospheric pressure. At 0 degrees Celsius, pure water, just water, nothing dissolved in it, is going to freeze at 0 degrees. But let's suppose I make a solution, a saltwater solution. The K constant now tells me that for every 1 molal solution, the freezing point is going to lower by 1.86 degrees Celsius. That's what this constant means. See those units? Degrees Celsius per molal unit. For a 1 molal solution, the freezing point will drop by 1.86 degrees Celsius. So water isn't going to freeze at 0, it's going to freeze at 0 minus 1.86 or negative 1.86 degrees Celsius. If I create a 2 molal solution, I've now depressed it by almost 3 degrees and so forth. So for every 1 molal, we affect the freezing point. Water, and again the word normal means standard pressure, normally boils at 100 degrees. Pure water boils at 100 degrees Celsius. If I create a solution of water, the boiling point actually raises, boiling points elevate, by 0.512 degrees. So a a 1 molal solution is going to increase the boiling point by 0.512 degrees Celsius. These constants have been experimentally determined, and notice how they're unique for every solvent. These do not need to be memorized, but they should be in a handy place for us to record and look up to solve problems. I believe in your notepad you're being asked to do that very thing. Examine the table: benzene, carbon tetrachloride, chloroform, ethanol, diethyl ether, and water, the common solvents. Some are polar, some are nonpolar. Take a time to record the normal freezing point, the Kf constants, the freezing point depression constants, the normal boiling points, and the Kb, the boiling point elevation constants, just so you have them handy as we proceed to solve some problems. Start up again with your video lesson when you've recorded these constants. Well, let's take a look at an example. What is the freezing point of a 1.7 molar aqueous ethylene glycol solution? What is the freezing point of 1.7 molar aqueous ethylene glycol solution? That term aqueous is telling us something, that water is the solvent. Aqueous solutions dissolve into water, and the ethylene glycol is what we call the solute. The solute dissolves in the water. The change in the temperature of a freezing point can be found by knowing the molality of your solution, the proportionality constant called the freezing point depression constant for water, and I'm going to put this on and we'll talk more about it. I've hinted at it, the Van Hoff factor. How many particles dissociate from the solute? Now notice here, it's not really important right now, but it just lets me see the lesson when it is. C2H6O2, well, that's a non-electrolyte. A non-electrolyte means it doesn't dissociate. The Van Hoff factor will be 1. One particle remains intact. But it's just a habit. You'll always see me write M molality times the K constant times the Van Hoff factor, even if it's a molecule, because it's a good habit to form. This will not be 1 for any kind of ionic salt, but for molecules it will be a 1. Okay, so let's think about what we know. We want to know the new freezing point of this water solution. The molality was given to us, wasn't it? It's a concentration of 1.7 molal. Do you remember that freezing point constant for water? You wrote it just above in your previous slide. 1.86, the freezing point depression constant for water. We need that number to do this problem. And that number is in a unit of degrees Celsius per molal. Van Hoff factor is of 1. A molecular compound does not dissociate. 1.7 molal times the K constant, 1.86. Let's hit that. 1.7 times 1.86. Oh, shoot, my calculator turned off. I'll hit it again. Sorry. 1.7 times 1.86, and you find 3.162. Now keep in mind that's not our final answer. That's how much the freezing point changes by. We know the normal freezing point of water is 0 degrees Celsius. And again, that was from our previous slide if you didn't know, but I think we do. Water freezes here at 0 degrees. And that might be unique. Depending on what solvent you're using, we should know the normal freezing point. And if water freezes at 0, freezing points depress and it depressed by 3.162 degrees. This is my change in the freezing point, if you will. The new freezing point is 0 minus 3.162 or negative 1.62, negative 3.162 degrees Celsius. My solution will freeze at negative 3.162 degrees Celsius. Let's look at another. Reading with me, it says, calculate the molar mass of a compound if a solution of 12 grams, this looks like the solute mass, is dissolved in 80 grams of water. This is the solvent information. And it's freezing at negative 1.94 degrees Celsius. Oh, in this problem, they didn't make us look it up. Here's the KF provided. Well, let's get our bearings, what we know. The change in the freezing point, and I'm just going to say the change in temperature of freezing point, I tend to just write this. How much does the freezing point change by? So I caught myself just doing that. Our text uses this denotation, delta TFP. I guess I've just learned to kind of shorten that. The change in the freezing point. So we'll roll with that. We'll adapt. Is molality times the K constant times the Van Hoff factor. Because we're looking for a molar mass of a molecule, the Van Hoff factor is known to be 1. I like to write that. It's my habit. The Van Hoff factor will always be written even if it's a 1, a non-electrolyte value of 1. Well, the change in freezing point we know. If normal freezing point is 0, and it's now freezing at negative 1.94, how much did it change by? Well, it changed by 1.94 degrees. So the delta freezing point is 1.94 degrees. Remember, change is always a positive thing. 0 minus the change is negative 1.94. But that negative sign isn't part of this. It changed by 1.94 units. The molality of our solution is our target here. And the K constant, the freezing point depression constant of water, 1.86 degrees Celsius for every molal solution. In the first step, solve for the molality of our solution. Because hidden in there is moles, and hidden in moles is the molar mass. We have multiple steps here. Solve for the molality of our solution. And let's do that. Let's hit that out. I'll hit 1.94 divided by 1.86, and I get 1.04 molal. Step 1, solve for molal. Step 2, what does molality tell us? Well, the molality tells us the number of moles of solute per kilogram of solvent. How many kilograms of solvent are there? Well, here's our solvent. I see that it's 80 grams. So is right in a kilogram, it's 0.08 kilograms. Alrighty, so let's cross multiply. We have 1.04 times the mass of 0.08 kg kilograms. And now we've determined that to be 0.834, I'll just stop there, moles of solute. Step 3. Step 1, repeating myself, change in freezing point, divided by 1.86, pulled out M, molality. We cross-multiplied molality times kilogram, and we found moles of solute. Moles, maybe just a round little buddy might be helpful to see that. And this is something that should be familiar. Moles is moles over, or grams over molar mass. Round little buddy. Grams over formula weight is a mole. M-O-L for mole. Well, we know this. We know grams of solute and we know moles of solute. This is what we're being asked to solve for, the molar mass. Remember how much solute we weighed out? Right up here, 12 grams. We weighed out 12 grams of solute. The number of moles we determined, 0.083 moles. And we get our unit for molar mass as a gram per mole. So 12 divided by that previous answer, I've got 143.8 is our molar mass. 143.8 grams per mole, the molar mass of all solute. Now, some of us, and if you're like me, I can see this all in kind of one step and just kind of showing you it's just a preference. There isn't a right or a wrong way. But if I think about just looking at this here, the change in freezing point is molality times K times the Van't Hoff factor. Van't Hoff was 1 because it's a non-electrolyte, but I still like to write it. We determined the freezing point change to be 1.94. Now, all in this one parenthesis, I can define my molality. Molality is moles per kilogram. Moles is grams over formula weight. Grams over molar mass is a mole. Per kilogram of solvent is little m. What I'm trying to do is show us when I have molality, I really can see the target variable right there hidden in it. Grams over molar mass per kilogram of solvent. This whole thing is little m, molality of solution. So if you're like me and just want one series of number crunching instead of 3 separate steps, and it's just a preference, I look at this and said 1.94, the change in the freezing point, was equal to 12 grams of solute over X, my target variable, the molar mass, per kilogram of water. The kilogram was 0.08 kilograms. See how I have moles per kilogram? All is my little m. Pull out the X, and you've done in one setup the series of 3 steps that we've done up above. Just depends on your algebra preference. Just thinking of key sequence, 1.94 times 0.08 is equal, and then I'd have the X. So hang on, let me just erase that. We have to put here, I have the X as well. So I have 1.94 times 0.08 times X is 12 times 1.86. These two end up on the right side, and those end up on the left side. Depends on your algebra skills, how much algebra you want to kind of play with. 3 separate steps are all together, but I bet we get the same thing. I can hit 12 times 1.86 equals, divide by 1.94, divide by 0.08, 143.8. So I got it both ways. 143.8 in one big algebra sweep. .08 and X go to the left. 12 times 1.86 go to the right. So all in one step or 3 separate steps. It honestly doesn't matter. It gets you there in the same direction. Calculate the molar mass, knowing the freezing point change. The molar mass is hidden inside the molality unit. I strongly recommend pausing, digest this problem, make sure you can do the same steps, and when you've mastered, continue on. Let's try some boiling point problems. The boiling point of a solution is higher than that of the pure solvent. Boiling points elevate. The difference between the boiling point of a solution and the boiling point of a pure solvent is directly proportional to the molality of your solution. The change in the boiling point is molality times the constant, the proportionality constant, times the Van Hoff factor. The Van Hoff factor, and I know it's coming up, I'm just kind of seeding that lesson, how many particles dissociate in solution. The more and more particles, the more we affect the boiling point. The KBs are a constant that depends upon the solvent. We spent time earlier in the lesson recording the constants. 0.515 is the boiling point constant for water. Now I say that, and it might be 0.512. Yeah, our book records it as 0.512. I memorized it as a student 1,000 years ago as 0.515, so I'll stick with 0.512 to be consistent. Let's model one of these problems. The math, again, very similar to the freezing point, except now boiling points increase, freezing points decrease. How many grams of ethylene glycol must be added to a kilogram of water to make the solution boil at 105 degrees? The change in the boiling point can be found by knowing the molality, the boiling point constant, and the Van Hoff factor. This solute is a non-electrolyte. Its Van Hoff factor is 1. It does not dissociate. So since the Van Hoff factor is 1, some texts will just drop it out. I like to be consistent and write that little Van Hoff factor, the number of particles that dissociate, even if it is a 1, just to set the habit of counting. Water normally boils at 100 degrees. It's now boiling at 105. How much should it change by? Well, I can see it elevated by 5 degrees Celsius. Alrighty. The molality times 0.512, the constant for water, times the Van Hoff factor of 1, the non-electrolyte. Step 1, solve for molality. The change in the boiling point was 5 degrees, divided by 0.512, the boiling point constant for water. 5 divided by 0.512 shows the molality of 9.77 molal units. Molality is defined as moles of solute per kilogram of solvent. 9.77 molal units, little m, molal. Let's pull out the number of moles per kilogram of solvent. That was a nice number, 1 kilogram. So mental math here, 9.77 moles of our solute, C2H6O2. Step 3, 9.77 moles of our solute times our molar mass. So we have for every 1 mole, how many grams? I think I might have added that earlier. 12 times 2 plus 6 plus 32. That's 62 grams of our ethylene glycol. 9.77 times the molar mass, and we have grams. 9.77 times 62, I found 605.74 grams of ethylene glycol. What have we just determined? How many grams of the solute do I add to a kilogram of water to get it boil 5 degrees higher? To get my solution to boil at 105 instead of just pure water boiling at 100, it takes 605.74 grams of ethylene glycol. If you're like me, you can think of this in 1 step instead of 3. It's just a preference. If you'd like to see the same setup, think of it this way. The change in the boiling point, 5 degrees Celsius, is equal to the molality of the solution. Molality is equal to grams over formula weight. There's our mole unit, isn't it? Moles per kilogram of solvent. That's our little m, the molality of our solution. Little m, molality. Moles per kilogram times the boiling point elevation constant, 0.512 degrees Celsius per molal. Pull out x, and you've got the same answer. But this way I only have one setup, and for my mind it seems to work better. Just thinking algebra, 5 times 1 times 62 is equal to 0.512x. X, 0.512 stay on the right, 1 slides over, 62 slides over. Pulling out x, 5 times 1 times 62, divide by 0.512, and you've got x. Prove it to yourself and hit it. You're going to find the same answer for the molar mass, or the mass of the solute, 605.74 grams. This, my friends, is a preference. It's how your algebra brain works. Solve for molality. From molality, solve for moles. From moles, solve for grams. Or envision the very definition of molality and see hidden in there the target variable, the mass of the solute over the formula weight per kilogram of solvent. That's our definition of molality, however works best for you. Let's calculate the boiling point of a solution made by dissolving 1 gram of glycerin, C3H6O3, into 54 grams of water. The boiling point made by dissolving, so here's my solute, a Van't Hoff factor of 1, into 54 grams of water, which is the solvent. The change in the boiling point is equal to the molality times the boiling point elevation constant times the Van't Hoff factor, the number of particles that dissociate. And again, this is a non-electrolyte, still using those non-electrolyte examples, so the Van't Hoff factor is 1. You will see me write that because eventually when we start dissolving salts, the Van't Hoff factor will change, so it's just a good habit to form. We're looking for the change in the boiling point, so we need a molality. That change in boiling point is the molality unit. All right, molality, what is that defined as? Molality, we have, we have 1 gram. Let me erase that. 1 gram of solute, which is glycerin, C3H8O3, divided by its molar mass. Let me add that for us. I don't know it by heart. There's 12 times 3 plus 8 plus 16 times 3. Did you find 92? I did. Grams over formula weight is a mole. Mole per kilogram of solvent. Kilogram of solvent. 54 grams, that's 0.054 kilograms of water. Now, see what I've done? Getting a little bit shorter in the way I'm showing work. This is my definition of molality. Moles of solute per kilogram of water. Grams over formula weight is my mole. Mole per kilogram is my molality. I can multiply that by the boiling point elevation constant of water, 0.512 degrees Celsius per molal unit. 1 divided by 92 divided by 0.054. My molality simplified to 0.201, I'll just keep it like a 3, times 0.512. And now when I hit that, I found 0.103 in my final answer. That, remember, we're solving for our change in boiling point, so that's our degrees Celsius. Water normally boils at 100 degrees Celsius. It's being raised by 0.103 degrees Celsius. It nudged a little bit. The new boiling point is 100.1 degrees Celsius. And that's what we're being asked. Calculate the new boiling point. So a little bit, a gram of glycerin, which is like Caro syrup. It's a sugary syrup. People make rock candy from glycerin. Raise the boiling point a little. The fourth and final colligative property is osmosis. The flow of a solvent through a semi-permeable membrane, perhaps like a cell membrane, is called osmosis. It tracks water flow. When I have a concentration gradient across a semi-permeable membrane, we have a transfer of water from one side to the other. A semi-permeable membrane allows the solvent to pass through, but not the solute. Semi-permeable means it acts as a protective barrier, allowing certain things to flow in and out of the cell while keeping other things away. Osmosis, oops, I should carry on a little bit first. Osmosis really talks about a lot about in biology. When you have a semi-permeable membrane and you want to track water flow, we talk about osmosis, osmotic pressure. This will end up to be a calculation, but I also wanted to make a moment, and finally, I should have put this slide earlier, talked about the Van Hoff factor, I. Ionic compounds will produce multiple solute particles for each formula unit. And so therefore, when we have an ionic compound, it actually affects colligative properties, boiling point, freezing point, depressions. They actually are affected a great deal more by an ionic compound than by a molecular compound. If I take table sugar, C6H12O6, oh, Linda. If I take table sugar, C12H22, O11. There's my formula. Anyway, if I take this, I can see it's a non-electrolyte. It does not dissociate, Van Hoff factor of 1. If I sprinkle just ordinary table salt, notice how it dissociates. 2 particles come out, a Van Hoff factor of 2. If I take rock salt, which is what we traditionally put on our sidewalks and our driveways, it dissociates to give me 3 total particles, the Van Hoff factor of 3. Colligative properties say it doesn't matter what you put in, it matters the amount you put in. And therefore, these ionic compounds have a greater effect on the boiling points, freezing points, on these colligative properties we've been studying more so than molecular compounds, simply because they give me more bang for the buck. They're going to give me more particles for each unique amount I put in for the salt. I mean, I can follow the trend. Aluminum chloride gives me an aluminum and 3 chlorides, Van Hoff factor of 4. 4 times the effect on the boiling point as compared to molecular sugar. So that Van Hoff factor, you see why it was so important to keep writing that in our practice problems. What if I want to calculate a freezing point of a molal solution in water and it has calcium chloride. How much does the freezing point depress by creating a 0.05 molal solution? Remember that freezing point constant depression for water, 1.86 per 1 molal? What's the Van Hoff factor now in calcium chloride? CaCl2. I count 1 calcium and 2 chloride. The Van Hoff factor of 3. 3 times the effect on the freezing point as a non-electrolyte. 0.05 times 1.86 times 3. I found 0.279 degrees Celsius. Remember, we're not done. That's the change in freezing point. Water normally freezes at 0. It's depressed by 0.279. So the new freezing point is negative 0.279 degrees Celsius. We got it to lower a little bit, but keep in mind that's not a very concentrated solution. What if I had 0.102 moles of calcium nitrate in 9.27 moles of water? Calculate the boiling point of our solution. The boiling point. So we have the change in boiling point equal to the molality of our solution times the K, the boiling point constant for water, times the Van Hoff factor I. Calcium nitrate dissociates. Out comes a calcium and 2 polyatomic ions of nitrate. The Van Hoff factor gives me a total of 3 particles. We've got a little more work to do because they gave us moles of water. We need it to be kilograms. So that's an interesting twist. 0.927 moles of water. Well, let's see. I know the mass is 18 grams per mole. Oh, that's cool. So see how I can get moles to cancel and convert my moles of water to grams of water, mole times molar mass. Good problem. That's the same as saying 16.686 grams of water, which is 0.0166, that's enough decimals there, kilograms of water. That's our solvent, isn't it? So I was doing that because this molality is moles of solute per kilogram of solvent. They made us work for it. Molality is moles of solute, which here is calcium nitrate, per kilogram of solvent. 0.927 moles of water we had to work out is 0.016686, plenty of decimals there, kilograms of water. We are boiling, so the boiling point elevation constant, 0.512 degrees Celsius per molal, and the Van Hoff factor of 3. What's that new boiling point? Moles of solute, whoops, clear screen, 0.102 divided by 0.0166686, almost a ridiculous number there, of decimals, times 0.512, the boiling point elevation constant for water, times the Van Hoff factor of 3. I'm going to re-hit because I don't believe my answer. 0.102 divide by 0.016686 times 0.512 times 3. Yeah, that looks better. I have 9.39 degrees Celsius. That's the change in the boiling point. Water normally boils at 100. It elevated by 9.39 degrees Celsius My new boiling point, 109.39 degrees Celsius. Pause and digest. I really recommend working out the problems mentally so that when you see them again, those steps are familiar. What would the theoretical boiling point of a solution be if we dissolved 10 grams of salt into 54 grams of water? Oh, another good straightforward problem. A change in the boiling point is molality times the boiling point constant for water times the Van Hoff factor of sodium chloride. Molality is moles per kilogram. Moles is grams over formula weight. Our 10 grams of sodium chloride set over its formula weight of 58.44. That's our very definition of the word mole, grams per formula weight. Moles per kilogram of water. This entire parenthesis is the concentration unit as molality. Moles per kilogram. So all in one parenthesis, I'm just kind of setting up the algebra to determine the concentration unit molality. Grams over formula weight gets me to moles. Moles per kilogram is my molality. The boiling point constant for the elevation of water, 0.512 degrees Celsius molal. And let's see, Van Hoff factor of sodium chloride, 1 sodium, 1 chloride, gives me 2 total particles. How much is the boiling point going to raise? Well, I hit 10 divided by 58.44 divided by 0.054. And if you hit equal, you get 3.1688 or somewhere around there. There's our molality. Times 0.512 times a Van Hoff factor of 2. And I found 3.245 degrees Celsius. Water normally boils at 100 degrees. It elevated by 3.245 degrees. The new boiling point, 103.245 degrees Celsius. You should pause the video and try these problems on your own, and then when you're ready to check, click play and see what you get. See if they're matching. Change in the boiling point is found by taking the solute ammonium sulfate, ammonium with its +1, sulfate with a -2, so we get NH4 taken twice, SO4. We're going to take 20 grams of ammonium sulfate, drop it into 75 grams of water, and tell me what temperature that solution would boil at. Boiling points raise when we add a solute. Well, we need the molality, so we have a little molality work to do. We have 20 grams of our solute, NH4 taken twice. Let's see, 14 times 2 on the ends, plus 8 for the H's, 32 for the sulfurs, 16 times 4 on the oxygens. I got a molar mass of 132 grams. So here's my mole. Mole of solute per kilogram of solvent, which is the water here. Grams over formula weight is moles of ammonium sulfate per kilogram of solvent. We'll hit The boiling point elevation constant for water, 0.512. And the Van Hoff factor, let's see, two groups of the polyatomic ion ammonium plus one more group of the polyatomic ion sulfate gives us a Van Hoff factor of 3. Two positive ammoniums and one -2 sulfate is a total of 3 particles. How much did the boiling point elevate by? 20 divided by 132 divided by 0.075, and my molality simplified to 2.020202 times 0.512 times 3. And that change in the boiling point, molality times 0.512 times 3, gave me a product of 3.103 degrees Celsius. Water normally boils at 100. It elevated by 3.103 degrees. Our new boiling point, 103.1 degrees Celsius. Here's a repeat slide. The osmotic pressures would have been a good time to introduce that after the Van Hoff factor, but at least now we know the fourth and final colligative property, osmotic pressure. The amount of pressure needed to keep the osmotic flow from taking place is called the osmotic pressure across a semi-permeable membrane. The good news here, I really do think that this is a nice review of a PUV-NERT problem. And here's what I mean. Pressure can be in terms of a flow of water. And if we're measuring not necessarily gas pressure, but water pressure across a semi-permeable membrane, we get something known as osmotic pressure. But that can be P in a PUV-NERT problem. Pressure typically is measured in an atmosphere. Volume is typically measured in a liter. N stands for the number of moles. R is our gas constant, and that's in a unit atmosphere liter per Kelvin mole. And of course, temperature is in a Kelvin unit. If I think about PV equal nRT and a way to manipulate this to solve for just pressure, what if I divide both sides by the volume to cancel out the liter unit? Now, I'm just kind of erasing the volume by putting it underneath, just to isolate the pressure. Mole times R times T. Here, think about it. nRT, that's the NERT divided by V. So if I rearrange, pressure is equal to nRT over V. Mole times the gas constant times the Kelvin temperature over the volume in a liter. Well, the very definition of molarity is moles per liter. Moles per liter is big M. The pressure is molarity times the gas constant R times the Kelvin temperature. And since pressure typically for the ideal gas chapter, PV equal nRT deals with gases, PUV equals NERT. But in this situation, switch we're tracking water, pressure gets a different symbol. It's pi. Now I know small pi and large pi look the same, except one's larger. So this here is a capital Pi in the Greek world. Pi is directly proportional to the molarity of our solution. Notice, very important, osmotic pressure, not molality, but molarity, moles per liter. If you can remember PUV-NERT, you can remember osmotic pressure problems using the ideal gas constant R of 0.082. Well, I memorized it as 0.0821. Osmotic pressure thinking about just a picture here. Here's a semi-permeable membrane in which water molecules can transport across very readily, but the solute particles are prevented. So notice in the first picture, I have water on one side and a solution on the other. There's a combination of molecules, so a solution is both particles. It tracks water flow. Water will move from high to low concentration. The salt is trapped in one side only. A semi-permeable membrane will have the water flow in the direction from higher to lower concentration. And you can see, really, this is just a U-tube, an open tube to the atmosphere. The water pressure pushes from the right side of the U-tube up towards the left, and notice how the water is actually climbing in that manometer. Osmotic pressure, the push of water from high to low concentration, can be calculated by saying pi equal MERT. Pressure is equal to molarity times the gas constant R times the Kelvin temperature. Let's find the molar mass of a protein if 5.87 milligrams per 10 mils gives an osmotic pressure of 2.45 torr at 25 degrees Celsius. All right, so I'm a beginning student. Here's all I know. PUV equals NERT. And actually, that's a pretty powerful PUV NERT. You know what? I don't even care if we memorize pi equal MERT or PUV equals NERT. To me, they're the same darn thing. It's just a manipulation of variables. Here's what I actually know. N is the number of moles. So hidden in my PV equal nRT is my target variable. The molar mass is what we're being asked to solve for, and that's this right here, hidden in the N of a PUV NERT. Oh, it's right there, hidden in molarity, but I see it a little quicker here in a PUV NERT problem. In a PUV NERT problem, PV equal nRT, P is pressure. Here it's given me as 2.45 torr. Now, this might be a good margin note because our constants, and they have to match the pressure. They have to match that unit. 62.4 if pressure is in a torr. 0.0821 if pressure is in an atmosphere. And it's 8.31 if pressure is in a kilopascal. I, for whatever reason, grew up memorizing the three different R constants and just made sure I matched the pressure unit by selecting the correct torr. Now, the other approach to that, and some teachers will have you do that, is to always, always, always convert your pressure to an atmosphere and just remember one R constant, 0.0821. It's whatever is the helpful for you. I'm going to choose to just leave it as 2.45 torr. The volume has to be in a liter. PUV NERTs always have to be in a liter. So it's given me 10 millis, which is 0.01 liters. The grams, well, here I have a milligram, so milli is 1,000, so I got to make it a smaller. 0.00587 grams over our target, X, the molar mass. R constant, I'm going to match to the torr unit, 62.4, and the Kelvin temperature of 298 K units. Let's pull out X. 2.45 times 0.01 liters times X is 0.00587 grams times 62.4 R constant times 298 Kelvin units. X 0.00587 grams times 62.4, the R constant, times 298 Kelvin units over 2.45 times 0.01. Let's see if we can't hit for the molar mass of this very large protein molecule. I expect it to be quite a large number. Proteins are enormously sized molecules. 0.00587 times 62.4 times 298 divide by parentheses 2.45 times 0.01. I'm showing 4,455.25, I'll round, grams per mole, the molar mass of this protein, which is not a crazy number. It seems huge to us that this formula weight could be 4,000 and something, but these molecules are actually thousands and thousands of atoms long, so that's a very reasonable number. We PUV-NERTed, good old days of a PUV-NERT where molar mass was our target variable. Pi equals MERT. That's really what the textbook will show you, but it's nothing more than a PUV-NERT problem. A lysosome is an enzyme used to cleave cell walls. A solution made by dissolving 0.075 grams of the enzyme called lysozyme in 100 mils of solution results in a pressure 1.32 times 10 to the negative third atmospheres at room temperature, 25 Celsius. What's the molar mass of our lysosome? Now, you might be considering pi equals MERT, but I'm a one-trick pony. I like to just memorize PUV equals NERT. It's just much more fun to say. Let's PUV-NERT it. Pressure, 1.32 times 10 to the negative third atmospheres. Volume must be in a liter. 100 mils is 0.1 liter. And the number of moles is grams over molar mass, our target variable. That's the N, isn't it? Grams over formula weight. Well, that's what we want to find, the formula weight of the lysozyme. R is the constant. Now we're in an atmosphere. What's the R constant that matches an ATM? I memorized it as 0.821, close enough. And the room temperature in a Kelvin unit, 298 K. So remember, we have to convert these to kelvins. Solve for X. 0.075 times 0.0821 times 298 Kelvin units divided by 1.32 E negative 3 divided again by 0.1. We got 13,901 grams per mole. The formula weight of an incredibly large enzyme, thousands and thousands of atoms long, not an uncommon weight. Osmotic pressure, PV equal nRT. Boiling points and freezing points, very similar math, where the change is calculated by molality times the K constant times the Van Hoff factor. And the fourth colligative property we discussed, but it's not a mathematical calculation, was vapor pressure. So as we end the journey of our solutions and colligative properties chapter, congratulations, you've accomplished quite a lot. I strongly encourage you to practice the homework problems. Practice these problems to where the steps become familiar with you. The more you practice, the more efficient you become. I hope you had a great Christmas break.